Hello everybody, welcome to the course VLSI Design Flow RTL to GDS. This is the 38th lecture. In this lecture, we will be continuing with chip planning. In the earlier lecture or in the last lecture, we had looked into some aspects of chip planning. We had looked into hierarchical design methodology, and we had also looked into some concepts related to floor planning. So, in this lecture, we will be continuing with some more concepts related to floor planning, and then we will be looking into power planning. So, during floor planning, one of the most important tasks is to place large objects. So, these large objects are also known as macros. Okay. So, now what is a large object or macro? So, these large objects can be the blocks, right. So, in the last class we had discussed that when for a big design we do a kind of partitioning, and after partitioning we get blocks, right. So, the blocks that we got, so at the top level those will be large objects that needs to be placed over the layout. So, the block obtained from partition, then there can be some other circuit elements, for example, RAM, ROM or analog components or larger, say, large clock buffers and so on. So, these are large objects which needs to be placed on the layout. So, we undertake the placement of those objects during floor planning stage, right. But remember that our design also contains, say, millions of standard cells, right. So, the standard cells, those will be placed on the layout or in the proper rows of standard cells during the placement stage, right. So, during the placement stage we are placing standard cells, the placement of standard cells, the word cell is missing here. So, the placement of standard cells is undertaken during the placement step or task, which will be done after chip planning, right. So, during chip planning stage we only place larger objects, right. So, why do we want to do this differentiation of larger objects versus smaller objects like standard cells? So, the difference lies in the scale, right. For example, in our design there can be, say, millions of standard cells, but macros or bigger objects can be, say, tens or maximum hundreds of them, right. And when the number of objects are smaller, we can manually see that whether the placement of the larger object has gone wrong, and therefore, a lot of manual intervention can be made during the placement of larger objects. But for standard cells, since they are millions, thinking of doing some manual intervention, it is more difficult or impossible for all the objects, but for some tweaking we can do, right. But we cannot get a global view of what the placement is for the standard cells and then do some manual intervention, that is very, very difficult, right. So, but for the placement of larger objects, a lot of manual intervention can be made, and that is why we undertake that during the floor planning stage. Additionally, the placement of these larger objects leads to a large or impacts the figure of merit or final figure of merit of our chip significantly, and therefore, the placement of larger objects must be undertaken more carefully than, say, standard cell placement. So, how do we place these big larger objects? So, the initial macro placement or large object placement is guided by connectivity, meaning how one block or one bigger object is connected with other bigger objects in our design, and based on that we can make some decisions, like for if there are two macros are connected or well connected strongly, meaning that many nets are going from one macros to another, then probably we can place them together or in the vicinity, right. So, the typically physical design tools have a feature of showing the fly lines, right. So, what are fly lines? Fly lines basically show as a number that how many nets are going from one object to the other. For example, suppose let us take this is just an indicative fly line for a design. Suppose there are say objects B1, B2, B3, B4, B5. These are 5 macros, right? And then there are IO cells, right? Now, these fly lines are indicating that how many nets go from one block to other. For example, if we say that consider this fly line, right. So, this fly line is going from B4 object and going into IO cell. So, that means that this IO cell, let us call it I1, and block 4 B4, these two are sharing 4 nets, right, and that is why the weight here is shown as 4, right, and so on. Similarly, if we look into that how many nets are between the object B2 and B5, we see that this is the fly line corresponding to them and there are 4 nets only, right. Now, using these fly lines, we can get some idea or clue that how the macros should be placed. For example, if we see the block B2 and the block B1, right. Now, between them how many nets are there? There are 52 nets, right, and among all of them this is the maximum, right. So, it gives us a hint that B1 and B2 must be made closer together, right. So, this is just a heuristic and based on that we can start with say initial floor planning and then probably modify or improve it and get to a better solution. Similarly, we can use for we can look into that how macros are connected to IO pads and IO cells, and based on that we can think that to which IO cell I should which IO cell I should put given a block or given a macro, it should be placed closer to which IO cell depending on how many nets are there between the block and the IO cells. For example, in this block 16 nets are between this cell and this cell, between block and this I cell, input output cell or IO pad, we can call it a I2, right. Now, this is a large number and therefore, we can think that B1 would be good if we can place it closer to I2 compared to some other IO cell. For example, the other IO cell is this 5. Now, this shares only 5 nets, right. So, this between B1 and this IO cell, let us call it as I3, there are only 5 nets. So, it is okay if we keep it further apart from I3, right. Now, additionally what we can do is that once we have an initial floor plan, right, we can do a kind of rough routing or predictive routing, right. So, these physical synthesis tool or physical implementation tools have some mechanism to do initial routing, right, a rough routing, right. It is not a very good in the sense that in the quality of routing is not important, but it is very fast and it gives some idea that where the congestion will be there in our design and so on. And based on that we can tweak the placement of these larger objects. Now, for the macro placement there is no very good algorithm as such, deterministic algorithm, and therefore, as a designer we often rely on guidelines to arrive at a good floor plan. So, let us look at a few guidelines that we can use in our design to improve the quality of our layout. So, one of the guidelines is that we allot contiguous region for standards, right. Suppose this is what these are A, B, C, D, E, F, G, H, these are the macros and this is the layout. This is the layout which is shown here, right. The spaces that are left over that will be finally filled by say standard shell. Now, in this layout, in this floor plan, we see that there are blocks of regions or non-contiguous region or fragmented regions where we are allocating space for the standard cells, right. These are the spaces where we are saying that we will put standard cell, and it is non-contiguous or fragmented. So, compared to this floor plan, if we consider another floor plan, we have just moved the blocks somewhat and created a continuous region or contiguous region for the standard cell. So, we should prefer this kind of floor plan over this one. Why should we prefer? Because in this case the area is same for the standard cell, area is same for in both the floor plans, but in the second one we have a continuous region. Now, the placement of standard cells is done using automatic tools, right, as we have discussed, and these automatic tools use algorithms, for example analytical placement algorithms, which work very well if the region is continuous. If it is fragmented, then the placement algorithm do not work well, right, and therefore it is always a good idea to allot a contiguous region for the standard cell as shown in this figure. Another guideline is that we should avoid narrow channels between macros, right. So, for example, consider this floor plan. In this we have a narrow channel region here, narrow channel region here, and also there is a narrow channel region between the macro and the edge of the floor plan, this, right. Now, we should avoid this kind of floor plan. Why? Because the first thing is that if the channel is narrow, right, then the number of routing tracks that will be there. You have routing tracks are parallel tracks, right. So, depending on its width, we can have that many number of tracks. Now, if this width becomes very small, then the number of routing tracks that will be available in a narrow channel will be much less, right. For example, here the number of routing tracks will be very less, right, and therefore, there will be a crunch of routing resources, and therefore, it is highly probable that there will be congestion in this narrow regions, narrow channel region between macros or at the edge of the floor plan, right. Another reason why we should avoid is that if we keep this region empty, right, if we allow any standard cell to be placed in that region, what may happen is that the placement tool might actually place cells here also, right, in these narrow channels. But since these channels are very narrow, later on if some optimization is required and if this cell size needs to be increased, there is no space left for increasing the cell size, right, and therefore optimizations will be hit, right. Optimizations and fixing timing problems for this kind of layout can be more difficult, right. Even upsizing will be difficult, or if the tool wants to insert buffers in these channels, that will also become difficult, and therefore, it can lead to timing violations and other kind of problems in the design. So, we must avoid this kind of narrow channels in our design. Then how to make our layout in this case, or how to make the floor plan in this case? One way is to we shift this up, and this narrow channel goes away, and whatever was the extra area available we have here, right. Now, this may not be that much narrow, and therefore, upsizing and say a congestion problem can be solved, right. So, upsizing can be enabled, insertion of buffers can be enabled, and congestion can be probably alleviated or will be less in this kind of floor plan. Another solution could be, right, if B is allowed to be is a kind of a object whose aspect ratio can be changed, right. Suppose B was a macro which we call as a flexible macro, right. So, there are two types of macros, right. So, there are two types of macros or large objects that we handle in floor plan. The first one is known as hard macros. These hard macros we might be getting from some other vendors, and in this case the aspect ratio and other things are fixed. We are not allowed to make any change in the area or the aspect ratio of the macros, right. But there are some macros which are known as flexible macros. Flexible macros. For these kind of macros, what happens is that we are allowed to change its aspect ratio, keeping the area same, right. So, if suppose B was a flexible macro, right, in that case we can probably resize it or change the aspect ratio, we make it longer, taller and thinner or less wider, and we can get rid of these narrow channels, right. So, if that is allowed, then we should do this, we can fix this problem of narrow channels by changing the aspect ratio of the flexible blocks. Now, let us look into some more guidelines. Now, first we can add halos around the corners in the floor plans. Now, what are halos? Halos are placement blockages where we do not allow any object to be placed. So, let us understand that why do we want to add halos in the corners of our macros, right. So, let us understand that what is the problem there. So, suppose this is a part of a floor plan, not a complete floor plan, but a part of the floor plan where we have highlighted the corner of this macro. There was a macro, right, and this is the corner of this macro, right, and if we do not add a halo, what can happen? So, understand that the macro is already designed, it may be a block which has been designed by another team, we got it, or this macro was a hard macro and we got it from some vendor or so on. So, this macro is designed and all the routing resources above the macros, so above this region, all the routing resources, meaning that 8 or 10 layers of interconnect may be there, all might be used for routing, right, and therefore, no routing resources is available over the macro, right. Now, suppose there are some cells which are placed around the periphery or around the corner of this macro. Now, if a routing of those objects or cells are needed, then all of them must go along this periphery. They cannot go over the macros, right, because over the macro routing resource is already used up. So, all the routing will be done around this macro, right, like this and so on, and therefore, a congestion will develop around the corner of the macros, right. Now, this problem gets aggravated if the cells are placed close to the corners of the macros, right. The routing of those cells, then on one side, on this side of the macros, those routing resources are not available, and therefore, they have got a restricted routing resources for the cells which are close to the corners of the macros, and therefore, we should avoid placing the cells near the corners of the macros, and to avoid that we create halo regions. So, halo regions are something we give as an instruction to the physical design tool, right. We say that on the layout, this is the halo region, do not place anything there, right. This is an instruction to the physical design tool, and then no standard cell will be actually placed in this region, and therefore, the problem of congestion will not come, right. So, this is why the halos are sometimes used in the floor plan. Additionally, what we can do is that we can use a lot of flexibility that are available during floor planning. Now, what are those flexibilities? The first is related to orientation, right. Now, we are given a say block, right. Now, given a block, what we can do is that we can either we can rotate it in 90-degree, or we can also take its mirror image either in the x axis or y axis. So, given an object, we can get different orientations, right. In fact, we can get 8 different orientations for a given macro, or say even for a standard cell, right. For example, suppose this was the macro, right, this was the macro, we had pin A, B, C and D, right. Now, if we take a reflection along the x axis, or let us x axis be this side, right, then we get another orientation, right. We will get C, D, A and B, right. So, so this was the macro and we got another orientation of this macro by rotating it, right. So, this will be M will become W, right, because of rotation. So, given a macro or an object, we can try out all different 8 combinations of orientation that are possible by the rotation of this of the object by 90-degree clockwise or 90-degree anti-clockwise, or we can try out the reflection along x axis or reflection along y axis, right, and therefore we will get 8 different orientation and we can choose the proper orientation. Only thing that a warning here is that once we rotate an object, the power lines also get rotated or reflected and so on, right. Now, whether the power lines in the object, where those are aligned, still aligned with the power grid that we had designed during power planning or not, that must be looked into, right. For example, if there is an object, we rotate it by 90-degree, the power lines which were running horizontally, now they are become vertical, right, and the orientation of those power lines may not be well in line with the power grids that we have designed. So, if when we change the orientation of the object, we should see that the after the new orientation, the power lines are also aligned. Then we said that there are some objects which are flexible objects, right, meaning that their aspect ratio can be changed. There are many blocks whose shape can also be changed, right. Rather than a rectangular shape, they can have a rectilinear shape. For example, this is a rectangular shape, right. Now, the same thing, same area can be same object can be reshaped and made in the form of say a L kind of shape, right. Now, this is a rectilinear shape, and this is a rectangular shape. Now, for a given a macro, we can, it is for many macros, it is not required that it should be always rectangular. It can be rectangular, it can rectilinear. For example, it can be L shape, it can be U shape, or any other shapes that we get by straight lines, right. So, we can try out different shapes and then see which one is giving us the best QR. Then we can try out different pin assignment, right. Now, suppose this was a flexible macro and there are pins that A, B, C, right. Now, if this is one case and it may happen that A is actually going to many objects which are lying at the bottom, right, and therefore, it may make sense that rather than having pin assignment as A, B, C, if we make it as say B, C, A, then the wire length can reduce, right, wire length can be reduced, right. So, we can also try different pin assignment for after doing floor planning to improve the QR. For example, in this the length of the wires can be probably reduced by trying out different pin assignment, right. Now, during floor planning, we also need to allocate regions for standard cells rows, right. So, in the earlier lectures, we had discussed that standard cells have a fixed height, right. All standard cells have fixed height, meaning that given a library, all gates, for example, AND gate, OR gate, inverter and so on, all will have the same height, but their width can vary, right. So, if they are of same height, we can arrange them in the form of a row, right. Now, and what is the height of this row? The height of this row is same as the height of the standard cells, right. Now, in some libraries, in some cases what can happen is that the standard cells can have different cells can have different heights, right. So, in that case we can make rows of different heights, right. So, multiple rows of different heights can be created when there are cells of different heights in the library. Usually it does not happen, but in some cases we might have cells which are of multiple heights, maybe height h1 and h2, right. Then you will need to create two different rows, one of height h1 and another height of h2. Now, standard cell rows are generally created by abutment. What it means is that we put one row of standard cell and another standard row of standard cell is sticking together, right, as shown here in close vicinity, right. Just one row is there and then the other row is there, and what another thing we do is that we create the rows such that the alternate rows are or the cells in alternate rows are rotated by 180 degree, right. So, in this row the row 1 VDD is at the top and ground is at the bottom, right. So, this is row 1, and in row 2 what is we have done is that we have made ground at top, this is ground and the VDD at bottom, and then in the next row what we have done is that again VDD is coming at the top and then ground is coming at the bottom. Now, what do we get a benefit out of this orientation? The benefit is that the same ground line can be used for both row 1 and row 2, right. So, row 1 and row 2 both are sharing the ground line, right, and row 2 and row 3 are sharing the VDD line, right, and so on, and therefore, we are saving the routing resources. Now, if there is a problem of congestion, then what we can do is that between say row 1 and row 2 we can open up spaces, right. So, we can open up routing channels can be created between rows to avoid congestion, right. So, this is these are some of the tasks that we carry out during floor planning. Now, let us look into the next task, that is the power planning. So, in power planning, first let us look into what are the major components. The first component is the power pads, right, the ones we had discussed in the last lecture, right. So, now power pads basically supply VDD and ground lines to the power delivery network. Now, from these are the power pads. In this case, I am showing there are 4 power pads, right. These light blue ones, those are ground power pads, and the dark blue ones are the VDD power pads, right. Now, from these power pads we have 2 rings, one ring for ground and another ring for VDD, right. So, the power rings carry power around the periphery of the die, right. Now, for this these ground lines or ground rings and power rings, which layers of metal do we use? Typically, we use the topmost layer, right. So, in the earlier lectures we had discussed that the thickness of the interconnects typically is larger at the top and lower at the bottom, right. Now, if the thickness of the metal layer is more at the top layer, it means that its sheet resistance will be smaller, and therefore, the resistance offered in the top layers of the integrated circuit, that will be lower, right, and we want that the voltage drop in the power lines is smaller, and therefore, typically we use the higher metal layers for the power rings and also for power delivery networks. So, from these power rings there will be power delivery network which will be created in the core area, right. So, we have power pads, right. So, power pads will get VDD and ground from the package VDD and ground pins, right. That will come to this power pads, and from power pads a ring is created, right, and the ring basically carries the VDD and the ground. Now, how many power pads do we need? That depends on what is the current requirement for our chip and so on, right. In this case, we have shown only 2, right, there could be many, right. Now, in the core area, we build a kind of power delivery network. Now, let us look into what is power delivery network. Now, the most common topology that we use for power delivery network is what is known as mesh grid topology, which is shown here, right. So, in this what is done is that there are parallel lines, these are parallel lines or horizontal lines, which are basically known as rails, these are known as rails, right, and there are vertical lines which are known as straps, right, and in between we have the connections which are vias, right, which connects these two, right. Now, these network or this mesh basically carries the VDD. So, this may be for VDD, there will be another mesh for say ground line, right, and from this power delivery network or mesh grid, the power power pins of the standard cells and macros, those will be driven and those will be tapped from these lines, right. So, this is how the power delivery network is created over the entire core area, and from the core, from this power delivery networks, from appropriate tapping points we get we get metal lines, and then that metal lines basically feeds to the ground and metal lines, ground and VDD lines of the standard cells and the macros. Now, what are the advantages of mesh grid topology? So, the advantages, the first advantage is that it provides or offers low resistance. We want that the power delivery network does not lead to a large voltage drop from the source to the end cell or the logic gate, and therefore, we want that the resistance should be low. So, the power delivery network which is of grid type, those grid type network offer low resistance. Why they offer low resistance? Because there are many parallel paths, right. Now, if there is a 2 points and there are more parallel paths between them, right, then of course, the resistance will go on decreasing as we create more parallel paths. Now, in this the mesh grid topology, there are so many parallel paths that the resistance, effective resistance between 2 points, that goes down. Another important merit of this power grid mesh grid topology is that it offers a high reliability. And why it offers high reliability? Again, the reason is similar, right. For example, given this point, there are, and suppose this one was the VDD line, VDD power pad. So, from this point to this point, there are many paths. For example, this path, this path, this path, and so many paths, right. Now, out of this path, say one of them gets snapped because of some problem, right, one of them gets snapped, then still the power will be delivered to this point through some other alternate paths, and therefore, this mesh grid topology has got a higher reliability, and it also leads to uniform current distribution, because this topology is more or less symmetrical, right. Now, depending on whether where the power the power pads are located, it may not be completely symmetrical, but if we just look at this grid topology, this is perfectly symmetrical, right. Other than say power variations due to PVT, power process induced variations and so on, that may change its symmetric nature. Otherwise, the current distribution will be more or less uniform in this case. Now, as a designer, when we are creating this power delivery network, what should we consider, or what important things we should need to consider? The first is that where these layers are, right. where this layer, this green line is one layer, right, and this orange line is another layer, right, where these lines should be. So, typically we will choose it at the higher level, higher metal layer. Why? Because the resistance will be lower in those metal layers, right. And then we need to also choose that how much width should be there between width of these metal lines should be there, right, and how much spacing should be there, right. Now, these are decided by the technology, right. So, for example, technology will say that you must have this much spacing between two lines, that is a design rule, this design rule that will come from the foundry, right, and similarly the width cannot be less than this and so on. So, these things will be decided by the design rules of the foundry. Additionally, we should consider that how much voltage drop is tolerable in our power delivery network, and based on that we can reduce the spacing between two parallel lines or so and take those decisions, right. Now, let us look into some of the problems that we need to uh, tackle or consider during designing a power grid. The first problem is related to electromigration. Now, what is electromigration? So, what happens that when the flow of current is unidirectional in metal, then it can actually lead to transport of metal mass in the direction opposite to the current flow, right. Now, if this is a metal and the current flow is in this direction, what can happen that the atoms of this metal that may actually move in opposite direction, and ultimately it can lead to circuit problem like short circuiting and open circuiting. Now, why does this happen? So, this happens because electron we can also consider it as a particle and it carries some momentum, right. Now, when these electrons are, when the current is in this direction, right, the current is in this direction, the conventional current is in the direction shown, the electrons are actually moving in the opposite direction, right, because electron carries negative charge and the electron direction movement is in opposite direction to the conventional current direction, right. So, the electrons will be actually moving in this direction, and these electrons are actually carrying momentum and those are hitting the metal atoms, and as a result of that the metal atoms can actually move from the location on the lattice from one point to the other, and it can lead to transport of metal mass. And when this happens, then we say that an electromigration has happened, right. So, because of these electromigration there can be short circuit or open circuit, and this kind of electromigration is more when the direction is unidirectional, meaning that current is always flowing in this. If it was also flowing in other direction sometime, then it can lead to a healing effect. That is what is observed in other kind of signals, where the current sometime goes in this direction, in some direction, sometime in opposite direction. Then the atom sometime moves in one direction, and in the other case it moves in the other direction. On an average, the metal atoms do not move, right, and that is known as healing effect. But what happens in the power delivery network is that the current always moves in one direction, right, from VDD to the element where it is supplying the power, right, and therefore, the direction of current is unidirectional, and power delivery network are more prone to electromigration, and therefore, we must consider this, that what for a given technology, given process technology, what is the tolerance limit of electromigration, and based on that we need to take some corrective measure. For example, we can increase the size of the conductor to ameliorate or decrease the effect of electromigration, or we can run tools which are report problems of electromigration, and they show that where there are current hotspots, and if there are current hotspots, then probably we can resize the conductor size or take some other measures to fix the electromigration problem. The other problem that is associated with the power delivery network is voltage drop problem. Now, first let us understand why there is a voltage drop in the power lines. The reason is the parasitic resistance and capacitance of the power lines. So, the power lines have got some resistance, right, or the power lines are made using metals as we have seen, and metals will have some resistance, right. Similarly, there can be inductance also, right, mainly between the package pin to the die, right. We have seen that in the last lecture, we have seen that from the package pin to the IO cells, there was metal wire, right, metal wires through which these things were bonded. Now, because of these packaged to die interconnection, there can be also inductance, right, and we know that because of the resistance and inductance, there can be a voltage drop. The voltage drop will be IR, that is corresponding to the I current, and R is the resistance of the line, and plus L di by dt. Whenever I is changing and there is an inductance, then because of L di by dt, there will be some voltage drop, right. Now, this voltage drop can be all during the static stage, meaning that when the active computation is not being done, or it can happen that in the dynamic stage, dynamic condition also. For example, when there is an active computation in our circuit, then a large current will be drawn from the power supply, right. And when large current is drawn from the power supply, this I component increases, so IR increases, and also di by dt can be sharp, because the current can go from 0 to some value very quickly in time, and therefore di by dt can be large, and therefore in the dynamic condition, the power in the dynamic condition, meaning that when the active computation is being done by the circuit, during that time a voltage drop, there can be a significant voltage drop in the power lines. Now, what is the problem of this voltage drop? So, the first problem is the performance, right. Now, if there is a voltage drop, then the standard cells, for example, if there is an inverter, right, and it was designed to operate was at 1 volt, right, 1 volt VDD, and this is the ground. But because of the voltage drop, it became, instead of 1 volt, say 0.8 volt. So, what will happen is that the delay of this inverter will increase, right. If the voltage supply supply to the standard cells, those come down, then the delay of the standard cells increases, and therefore, the signal propagation along the path that slows down, and the maximum frequency at which our circuit can operate, that comes down, right. And therefore, we need to perform voltage drop analysis in both static and dynamic condition. For example, dynamic condition, we can think of that when we subject our circuit to some simulation, or we apply test vectors to our circuit and does some active computation, and we do we get that the changes in the values of the nets for the design, and based on that we can understand that what is the activity in our design, and using those activity we can estimate that what will be the current drawn by from the power line, and therefore, if in some portion of our design or layout there is large activity, there a large current will be drawn, and there will be a higher IR drop and LDI by dt drop, and the voltage can come down drastically, right. So, those regions where in the layout where there is a large deviation from the stated voltage. So, suppose the stated voltage or the rated voltage or the nominal voltage was say 1 volt, right, and the voltage drop became, or during dynamic condition or during the working of the chip, it dropped from 1 volt to 0.8 volt, right. So, this is a large IR drop, and in the portion of the design where there is a large IR drop, those are known as IR drop hotspots. So, there are tools available which help us understand that which portion of our layout are IR drop hotspots. Then we have to take some corrective measures to fix those IR drop hotspots. And how can we fix it? We can fix it. One of the most popular technique is to use what is known as decoupling capacitor or decap cells. Now, what is a decap cell? Decap cells are capacitors inserted between power and ground lines. So, these are simple capacitors. We have say one line VDD and this is the ground line. Between this we have a capacitor, right. So, ideally what will happen, or no, in the static condition what will happen, this capacitor will be charged to VDD, right, it will be charged to supply voltage, right. Now, but when circuit does an active computation and a standard cell, for example, suppose with this VDD and ground line there was an inverter connected to it, right. This is the VDD line for the inverter, this is the ground line for the inverter, right. Suppose this inverter was drawing a large current, right. So, in that case these capacitor will act as local storage, right. So, the power line is, suppose the power pad is here, this is the VDD pad, this is the ground pad, right. So, rather than getting current from this path, if a local decap cell is there, then some current will also be supplied by this decap cell, right, and therefore, the power the voltage drop that is seen by the power lines, that will be reduced, right. So, what this decap cell is doing is, it is basically acting as a local charge storage, right, and these charge storage supplies charge to the standard cells, or in this case inverter. So, these decap cells supply charge whenever required during dynamic operation of the circuit, and this addition of these decap cells basically reduces the effective voltage drop that is seen by the standard cells, right. Now, where should we place these decap cells? So, we should place these decap cells at the strategic location. For example, if we know on the layout that these are the IR drop hotspots, if we put decap cells closer to those regions, right, closer to those IR drop hotspots, then these decap cells can provide local charge to those IR drop to the circuit elements within that IR drop hotspot, and the problem of voltage drop will be less or reduced, right. But what is the demerit of adding a decap cell? The demerit is that it increases the die area, right, because it takes some die area, it is a capacitor and therefore, it will consume some die area, and also it will lead to leakage power dissipation. Okay. So, we said that this decap cell will be charged to VDD, right, in normal static condition, but it will also have some leakage current, right, and that will be drawn even when the circuit is not operating, right. So, the leakage current of the circuit can go up because of decap, but still these two merits, despite these two demerits, we still use decap cells to fix IR drop hotspots, because it is very effective in solving that problem, and the cost involved can be kept low if we do it carefully, right. If we choose the number of decap cells carefully and use only when it is required, keep the size of the decap cells to the minimal that is required, and place them at the strategic location, then we will be able to utilize decap cells very effectively, right. Now, fixing IR drop problem can be actually done or tackled throughout the VLSI design flow, right. So, we can even take decisions at the system level, that if in our design, right, there are two modules which are drawing lot of current, right. So, we should power on those modules in a staggered manner, that the peak current of the circuit comes down and the effective IR drop seen by the circuit is smaller or reduced, right. So, even at the architectural level or at the system level also, we can fix IR drop problem, right. We will see that how in clock tree synthesis, by adding clock skew, we can solve the IR drop problem also, right. So, IR drop problem can be tackled at different stages in the VLSI design. So, if you want to know more about these topics, you can go through to these you can refer to this textbook. Now, to summarize, in this lecture what we have done is that we have looked into some more aspects of floor planning, and we have also looked into power planning, right. An important thing to note here is that during the chip planning stage, a lot of manual intervention is made, right, and it is a very crucial step, and the decisions of the chip planning impacts the complete physical design implementation, right. And therefore, we often tweak the solutions that we get out of the tool and make manual interventions, right. And therefore, EDA tools or commercial EDA tools provide many features and mechanisms which allows us to make those manual intervention more effectively and efficiently, right. So, if I will suggest that if you are using say commercial EDA tools, then look into the manuals and understand that what opportunities you have to get a better planning or to do chip planning more efficiently, right. Now, in the next lecture, we will go to the next major physical design step, that is placement. Thank you very much.